Good evening. Our speaker this afternoon is ECE Engineer in Residence, Dr. Corkudale, Michael Corkudale. He received his undergraduate degree from our department in 1997. Is that correct?
That's right.
And then he went to Michigan to get his advanced degrees. And he also received a prize last year, ECE Young Alumni Achievement Award in 2009 for his work on entrepreneurial leadership in technology commercialization and his academic and community service. So he formed a company and then sold it to a bigger company, and that is the story that he'll be telling us today. Then he will be answering any questions that you may have later after his talk, but he will be also available tomorrow. That is the ECE Engineer in Residence program that we are starting now. Tomorrow he'll be available in room 159 to answer your questions if you are interested in the kind of work that Dr. Corkudale has been following. So,
okay, great. Thank you for the introduction. So let's see. Can you hear me now? Is that clear? Okay, good. All right, well, thank you for the introduction, and thank you for attending. I had dinner with Andreas and where I live now with my wife in Palo Alto just a week or two ago, and I guess this is the first instance of the Engineer in Residence program, so I hope it doesn't become the last. I hope you actually take something out of this. You know, kind of being in technology and being an entrepreneur, you start to learn to talk without slides, but one of the things that Andreas and I discussed, and one of the concerns I have that you'll see me touch on here is, I think it's important for students to see real semiconductor work, hardware work, real true ECE work in a venture-backed business and now a part of a larger company. And in doing that, there's a lot of technology and pictures that I think will help tell this story a lot better. So otherwise, I wouldn't have bothered using slides, but today I will. And the point is that, you know, the company I'm going to talk about today and the business unit that I run today wouldn't be possible without my engineering background. And I think that's a good segue into the outline of what I'd like to discuss. I'd first like to at least sort of get you acclimated to my background so you understand the point of view from which I'm coming. And then I'll introduce our flagship technology, what we call CMOS Oscillator or silicon oscillator technology. I'll discuss founding Mobius Microsystems, the company I founded, and other related disasters. You'll see many different issues that we faced going through that process. And then the acquisition by Integrated Device Technology. And that's what I sort of dubbed this seminar as exiting back to operating a business unit. So we didn't exit and then just take all of our money and run. We exited, we did take our money, but we continue to run that business because it's an exciting business to continue to run. And at IDT, I think it's got a lot more legs to it. And I'll conclude with some things that you might find interesting. So my background is this. As introduced, I came here between 93 and 97. I finished my BSEE here. You can see actually me and one of my colleagues here being inducted into Eta Kappa Nu. He was actually the first employee at Mobius. What you can see here, I had a bigger picture, but my wife said to shrink it down. See, he's holding scotch here. I think having a scotch at an Honor Society induction is actually pretty darn impressive. So. And I think he still is holding a scotch if I were to call him right now. No, so we've had a good relationship for years, and he's still with us at IDT. And it's kind of a good example of you know, some of the memories I have here from Urbana-Champaign, because you know, one of the people that I met here and got to know is now a lifelong colleague, and I think you guys will have similar experiences. After being here, I went off and worked in aerospace for a while. I spent a year working on heterojunction circuit design at Hughes Space Communications. At that time, I had friends joining these you know, rapidly growing and actually, as you all know, later crashing .com businesses. And at that time, I was also a lot more interested in sort of core technologies and research. And I spent the better part of that year sort of thinking about the work I wanted to do, applying to graduate school and whatnot. And at the same time, don't forget, living in Los Angeles, there's nothing wrong with living in Los Angeles. It was a hell of a time. And through some sort of serendipity, I ended up going to Michigan or attending Michigan, and that was particularly because this faculty member, Clark Nguyen, he's a pretty well-known guy in the MEMS area. He's now at Berkeley, but he had recruited me to come there and work on frequency control circuits or oscillator circuits that were MEMS-based. He ultimately became the founder of Desera, which is actually one of our competitors. And through that process, as Clark got that company off the ground, I started to become very interested in research, commercialization, and startups. And at that same time, the dot-com bubble was imploding. This is around the 2000 timeframe. And VCs, or venture capitalists, were really turning their attention to fundamental technology. That's all you could hear in 2000 is, we don't want another pets.com, we want fundamental technology that's differentiated. And so, related to that, I started a new research program with Rich Brown. He's now the dean over at Utah. And we started to build this CMOS oscillator technology that had a lot of promise, and we started entering these different design competitions, business plan competitions, started filing patents. I was off taking business plan writing courses in the business school in the evening, and I got really sort of wrapped up into this idea that, hey, we might actually have a technology we could commercialize. And I've talked about that in other seminars, but this was, you know, I don't want to go into the details, but this is really where I sort of thought we can start a company. And so we did that. In 2004, I founded Mobius Microsystems. In that company, I played many different roles. I started as the CEO, where I raised the initial capital, recruited the initial team, got the initial design wins, even participated in the initial design. And then CTO was a role that I always played as the company grew, and I was kind of transitioning in and out of this role. Anytime I wasn't necessarily needed for the most imminent challenge, I would sit there and focus on technology direction and, you know, evangelism and things like that. And then there were times like we had a need where I sat in as acting VP of engineering, and of course what that means is, as I've written here, you know, this means that you know, there was something total debacle with our initial VP of engineering, which is pretty common. So I had to sit there in that role, and then of course I was replaced once another VP came in. The point I'm making here, though, is I went through all these different gyrations and cycles of you know, playing different roles in this organization in order to sustain it and to keep it growing. And then in 2010, IDT, or Integrated Device Technology, which is a public company, a semiconductor company, a fabless company, acquired us. They created this new business unit, which is now known as the Silicon Frequency Control Business Unit, or SFC Business Unit. We maintain our offices in both Ann Arbor and Sunnyvale, and I'm now the general manager of that business, and we continue to grow rapidly, and that's one of the main reasons that we continue to stay at IDT, to see how big we can make this business, which I think you'll see is pretty darn exciting. So this is you know, my overall experience to date. At IDT, we've had quite a bit of success. You can see some of the headlines here. This is an announcement of the acquisition, where we're expanding their timing market by $700 million. Here's Ted Tewksbury, our CEO at IDT, talking with EE Times, you know, describing our technology and how we double their served market. And actually, I was impressed. EE Times actually stood true to our startup nature. Just last October, I was introducing our new product, this 100 ppm or 100 parts per million CMOS oscillator product. And they even called out, you know, this was originally Mobius technology, and that we were the innovators here, despite it now being an IDT product. And then Ted, even that same month on his earnings call, on the transcript there, you can see that he was talking about our new technology and our new product that we introduced, and he calls it a breakthrough to the analysts, which I think was a pretty nice shout out for, you know, for a new product line at IDT. So let me introduce what that product is. You know, I've been mentioning this word timing. Let me describe timing. Timing is everywhere. So if you pick up, I'm sure many of you have an iPhone or a similar smartphone. If you take a look at the iPhone, for example, just on the main board, it has 5 different timing references. So these are quartz-based crystals that vibrate at a distinct frequency to support these different functions, be it power management, GPS, the application processor, the radio, and so on. And these crystal oscillators, if you're not familiar with them, they're actually, as you can see in this picture, they're sheets of quartz that are sandwiched between 2 electrodes. And they simply resonate. It's a piezoelectric material, so when you apply a field, it mechanically deforms and vice versa. So what happens is there's effectively this bulk mode where this sheet of crystal resonates at a distinct frequency. And then there's a sustaining circuit underneath, active circuitry. The technology is actually quite old. In 1880, piezoelectricity was discovered by the Curies. This is how long ago this technology dates. And then in 1917, this French scientist started using crystal resonance for sonar applications. And just 2 years later, these guys, Nicholson and Caddy, if you ever work in the frequency control space, there are awards named after these guys. These are the pioneering guys. They were the first ones to use quartz references for generating frequencies. And since 1919 to now, quartz crystal oscillators have proliferated. They've become the de facto standard in frequency control. Billions of units are sold and distributed annually. So it's a very large market, and the volume is extremely high. So is there any problem with this technology? Well, it's a very cost-effective technology through economies of scale, but it takes about 2 to 6 months just to grow this quartz crystal material in order to slice it down to those thin wafers. In terms of scalability, these quartz crystals have scaled historically. They used to be in much bigger packages, and they've scaled all the way down to very small millimeter scale packages, but the limits to that scaling are now imminent. Quartz is a very stable frequency reference, but quartz is still a rock. It's kind of a funny thing. If you pick up that iPhone board, you can see all these different technologies, radios jammed into a single piece of silicon, and yet you have these individual components that their only purpose is to generate a frequency. So it's a rock, and you need silicon for additional functionality. It's not a very functional technology. And although quartz is small, it can't be integrated. It's not what I would call siliconized. It can't be integrated into the other components that sit on these platforms. So it's really kind of been one of these great holdouts for microelectronic integration. The reason is quartz is very accurate and stable. Off-the-shelf quartz crystal oscillators can maintain 100 ppm or 0.01% frequency accuracy over all conditions. Quartz is also known as a high quality factor or high Q component. So that translates to very low noise and very low jitter, which are critical for many high bandwidth applications. And it's low power. In contrast, silicon technologies, they vary by 10% or more. So that's 10,000 ppm, talking about orders of magnitude difference in accuracy just due to manufacturing. They do not have high Q components and require more power. So like I said, quartz is really this last great holdout for microelectronic integration, and one of the reasons is there's such a difference in the performance levels between what quartz can achieve and what we can achieve with silicon. But despite that, the market keeps demanding something more from frequency control. The trends are these. Every new generation of a product increases in its bandwidth. So for example, USB 3, you'll start using these products. That's a 5 gigabit per second interface. Currently, USB 2 is 480 megahertz. So from one generation to the next, you're talking about a 10x change in frequency. And so that means frequency continues to go up, while quartz is limited due to its the mechanical manufacturing of the product and the resonant frequency that's associated with it. Similarly, as you know, products continue to decrease in size. So quartz now is very limited in terms of how much the size can scale, and the market is looking for products now that are 100 microns thick or 50 microns thick. These products can only be achieved with silicon. And last, quartz has no additional functionality. It's just a vibrating rock. So these market trends, there's a demand to meet these trends without giving up performance and without adding cost. And the reason this is so interesting, and the reason we got funded, and there's actually several other companies funded with competing technologies, is it's a $5 billion market. If you could go out there and replace quartz, you can make a lot of money doing it. It's a huge market with a big bullseye on its back. So we had this thinking at Michigan. Our thinking was, okay, let's look at developing an all-silicon frequency source. Let's find a way we could get rid of quartz. Let's first leverage advances in radio frequency CMOS technology. So I don't know if you're familiar with this, but in the late 90s, RF CMOS really took off. There was this thinking before that time that RF products had to be made in heterojunction technologies, in SiGe, and other exotic technologies. And many actually venture-backed companies focused on, can we make good performing products in CMOS? And to address that, companies like TSMC, Taiwan Semiconductor, and other foundries started adding new process options, high-Q inductors, metal insulator metal caps, and many other features that enable RF CMOS. So our thinking was, this is the right time to come back and think, can we build accurate silicon oscillators? Because now we have much better components to work with. We had to conceive of an architecture to achieve low frequency error and low phase noise and jitter. I mean, these are the sort of two critical parameters in order to provide an accurate frequency reference or an acceptable frequency reference. And we were focused on developing towards with an eye towards wireline timing. So examples are USB. There's an accuracy requirement of 500 ppm, or parts per million. Serial ATA, which is the hard drive interface, that's 350. PCI, that's the backplane interface in personal computers. But we also knew that quartz was sitting at 100 ppm accuracy. So if we could get to that level performance, it would really be a groundbreaking achievement. So this is a short diversion for those of you in the EE curriculum and those of you who will appreciate a little bit of circuits. The simplified architecture looks something like this. We free run a CMOS LC oscillator at several gigahertz. Then we wrap around it very high resolution process trimming and design open loop temperature compensation to maintain the frequency accuracy. We buffer the external supply by actively regulating it and then divide by a large factor. We frequency divide because frequency division pushes the noise down. And then ultimately we were aiming to develop a low jitter and stable frequency reference in the range where you see quartz crystals, 10 megahertz, well up to 50 and then beyond, extending to 200 megahertz or so. So this is a short and simplified schematic here. You see the LC oscillator with a cross-coupled configuration, sustaining amplifier, the cascode bias here, and then these are these thin film caps that were switchable. So essentially we program each and every device to trim the frequency back on, and then these varactors are tied back to temperature-dependent voltages that respond to temperature. So the idea here is this is to get the device on frequency and then to maintain its temperature accuracy. And then we take that core oscillator and we wrap around it a low dropout regulator from a band gap reference. Then the temperature-dependent voltages are generated and some other circuitry, differential to single-ended conversion, programmable divider, output buffer, sort of all the things to sustain the functionality of the device. And then some programming interface, I2C interface, and a few other functions, including non-volatile memory, something to store these trimming coefficients. So that's the brief overview on the, how the technology works. And again, I should mention something. You can read some of our papers. All the papers you read, this is how it is in industry. Everything you read is about 5 years old. So you'll see those diagrams. That's conceptually how things work, but that's not actually how our existing products work. But that being said, this is how the initial research prototypes we developed work. And so this is an example of one of the chips we built in 0.18 micron CMOS. Performance was very good, but not perfect. And we demonstrated very low phase noise and jitter as we predicted. So you see very low jitter here. This phase noise, actually, if you look up the numbers and compare it to the literature, it's very good. Similarly, we tested the frequency accuracy. So this is another critical dimension. And here you can see over temperature, we have about 2,500 ppm accuracy. And this is an interesting benchmark because this is the requirement for full speed USB, which is the early generation of USB. So back then we were thinking, well, this is interesting. We're right on the cusp of being able to achieve that. It looks like we have a technology that can actually do this and replace these quartz crystals. We took it even a step further at Michigan. We embedded this clock generator into a microcontroller. So you can see the clock generator here as an IP macro. We implemented in this processor at Michigan called the WIMS processor. It's a 16-bit microcontroller. And we showed that the clock would occupy only 0.3 millimeters squared in a 1/8 micron CMOS, which is less than 3% of the total die area. And it was another demonstrator where we could say, here, we have a silicon technology that we've demonstrated, integrated into a larger chip and therefore you can replace the external crystal. So by 2004, and by my defense, we had this. We had the discrete CMOS oscillators in hand. We could show decent frequency accuracy and good phase noise and jitter. We also had the CMOS oscillators as an IP block in a microcontroller. And of course, we thought, well, then it's time to start a company. We have everything. Well, yeah. For the next several years, we went through several revisions of the business model. We went through many unforeseen technical challenges and many different business challenges. But this is where we started from. So let me talk about that. As I mentioned, in 2004, I founded Mobius with my faculty advisor. And as you could see, the technology performance was as follows. The performance wasn't ultimate, but it was good enough to start. We had these samples in hand from my dissertation work. And we had actually filed quite a bit of IP and other things to kind of get the company going and make sure that we had a defensible position in case competition showed up. Our initial plan was to build an IP business. So an IP business in semiconductors is where you do the design or the blueprint, and then you sell or license that design to a customer so they can integrate it into their product. And the reason we wanted to do that was that the capital requirements were low and the value proposition was very strong. Imagine you have this microcontroller that would need that big crystal next to it. We could sell an IP block to someone, to a customer, they would integrate it, and then you wouldn't need this crystal anymore. So the value was strong. We raised about $2 million from a handful of smaller tier Midwest VC firms, and I went around personally and raised money from about 20 different angels, ranging from New York City to Chicago to Detroit, Columbus, all over the place. And started the company like anyone would out of university with university colleagues who didn't know anything and probably didn't know anything more than I did. But the fact of the matter is it was really the most exciting thing I'd ever done in my life. It's kind of just diving in headfirst into the wild blue yonder and seeing if we can actually accomplish something. And we did. The first thing we ran into was this product application. This is a controller that is used in a bridging cable. So you know, when you take these cables that connect your phone to your PC, for example, often the interface is not the same on both sides. So you'll see either some large plastic enclosure on the cable side or even a bubble inside the cable. This controller is what's sitting inside there to bridge the two interfaces. And this was a great target because here we have this big ugly crystal to get rid of. And we did. So here you can see we've rid ourselves of this crystal, and what we did is, this is our customer's chip, and then in the upper left corner here, this is our IP macro, or our design that we licensed to this customer. And this was the first high-volume commercial replacement of quartz crystal oscillators. You can see it's 0.18 millimeters squared in a 0.35 micron CMOS process. This was for full-speed USB. So 2,500 ppm in production, but we could build it at 500 ppm for high-speed USB. This product did 10 million units, and actually this is out of date. It's probably done over 20 million units, and it's still on the market and shipping to date. So this was the very first revenue that we were able to generate as Mobius, and we published this in, you can see the reference here in the journal Solid State Circuits. So this was a very big success, but it was an absolutely terrible business. So this is the problem with these IP businesses. We had very high NRE, or non-recurring engineering, for each new customer. So imagine this. Every customer has their design in a different foundry, different process options, different technology node. So every time we found a customer that wanted our design, we would have to port it or redesign it to that new foundry. The other problem was the IP revenue was loaded on the back end. So most of the revenue that was coming in is once we designed the product in, we were dependent on, can our customers sell their product, because we would take royalty off the products that they would sell. And we learned very quickly it's not a scalable business. IP businesses start to look like services business, and in the end the real nail in the coffin was no one would fund our business. So we had raised money, proved we could replace quartz, got a customer, had revenue, nobody gave a crap. It was a tough time. So what we did is we focused on writing a new business plan. We focused on how could we build components based on our technology? And to build a component business, by the way, we're talking about raising, you know, $20, $30 million to build an actual standalone product. And so I knew very quickly we weren't going to be able to raise money in Michigan, so I moved to California and was able to raise $10 million there. And by the way, that's one line item. Don't think that that's something that, don't think there's a correlation. You move to California and you just raise the money, right? It's really hard to raise money, especially for semiconductors. So I'm leaving a lot of details out. But I moved the headquarters to Silicon Valley, and we started to hire what we'd call a professional team. But actually, I didn't write it there. What we really did is hire a bunch of jackasses. And this is a typical thing, and I'll talk about it later. The reason is you take that amount of money, you know, you're coming out of graduate school or university, you've got all these young guys rearing to go, and the first thing the VCs want to do is de-risk it by putting so-called experienced management. And, you know, there is a thing about experience management that experience doesn't necessarily correlate to successful execution. So this was the worst time of my life. In contrast to starting it and thinking we could do anything, this was the worst time of my life. So the new management team basically said this. Forget what I wrote there. They basically said, you idiots from graduate school know nothing. So just get the hell out of the way and let us take your technology and get rich with it, and hopefully you'll go away or we can get you fired or something like that. And the way they went about this was kind of fascinating. They defined a product that required a 25x performance improvement from where we were. So I showed you we had that thing in production. It was shipping, it was generating revenue, and it was 2,500 ppm in production. So they said, look, if you want to play in this game, you've got to be at 100 ppm. Otherwise, it's 100 ppm or nothing. And then they went to the investors and said, that's how this is going to work. And so 2 years of development went by. We were just spinning our wheels, trying to get the, I mean, it's completely unrealistic goal. The analogy I make to people is the space program. What was the first thing we did in the space program? We put a monkey in orbit, right? We didn't go straight to the moon. So this analogy here with these guys, they were saying, okay, let's do this. Let's not even go straight to the moon. Let's just go straight to Mars. There was no sequencing of the technology risk. So, you know, a lot of different challenges could have been addressed, but, you know, they weren't because of all these other issues. And this was the kicker. I go on my honeymoon. The management team goes to the board and tries to get me fired while I'm on my honeymoon. So you can imagine getting a phone call on your honeymoon, and, you know, the chairman of the board says, we're going to fire you and all of your idiot friends from graduate school. Comment on that? And let's not forget, the only revenue this company ever had was the revenue from design wins I had secured and my team had executed on delivering product. All these guys, with all their wisdom, had never generated a penny of revenue for the company. So needless to say, the board actually stuck with me, which was a good thing, but you can imagine how stressful this was. And nevertheless, we did get a product finally done. This is our first component that we introduced. This is the Mobius actually wafer in quarter micron technology from Taiwan Semiconductor. This is the die micrograph for that product. It has all those different building blocks that I illustrated. And then this is the product brochure where we announced it at the Global Press Electronics Summit. And so this was the most accurate silicon oscillator that had ever been built. It was a 300 ppm product. We published it at ISSCC. It had the big auditorium and 1,000 some odd attendees. So it really made a pretty big bang that, hey, maybe silicon technology really can replace quartz technology. It might be possible. But we hadn't really thought it through all the way. We were thinking of it like this. We were thinking, this is quartz, right? This is kind of what you will see in legacy products. These are called, metal can quartz oscillators. And here's our silicon oscillator. That seems really awesome, right? But that's not really the state of the art. So there was another technology on the horizon, MEMS technology, that I mentioned I had been working on, our product, and this was the state of the art crystal oscillator. So actually, there was really not much differentiation. That's why that IP business was so neat, right? You could get rid of all this and you could stick it on the chip. But once you start making the components, what the hell is the difference between them, right? They all look the same. They're all in the same footprint, all same form factor. So it really was not a great business. And that's because it's replacement. So by definition, we don't enable anything with our technology this way. We're just stealing the socket. Remember with the IP business, we enabled something because we enabled you to eliminate the crystal. You could stick it into the SoC, right? That's something different. And quartz was still better than our technology. It still had better accuracy, better noise. We hadn't scaled to those performance levels. So the differentiation was very low. Competition was also showing up, which was a major threat. And the fact of the matter is no one was really all that interested in the product. It almost was a bit of a technology diversion, sort of saying, well, these guys continue to work on these silicon oscillators. They're making great progress. But in the end, you know, the proof in the pudding is where's the revenue? Is anyone buying it? So we were pushing, and there was very little pull. And this is a key thing that I think researchers and students need to understand, that when you do a technology-driven business, it's a push. You're pushing the technology onto the market, trying to find a place that it sits. The way industry works is it's always a pull. The customers are always telling you, this is the next thing I need. You know, I need 10x bandwidth on the next interface. I need, you know, half the power. So it's always being pulled by the customer. When you're coming as a startup, you're pushing it out there, and you have to find the socket that it sits into. But the thing that we were able to do here is we had samples, and we were able to engage the market. That was the key thing. So we rebuilt the entire management team, effectively fired everyone, got a new CEO. I couldn't believe it. We raised $16 million on a wing and a prayer, and frankly, what I think was complete bullshit. But somehow, people gave us money. So give some credit to VCs. They at least believed in us. And we focused on differentiation. That was our thinking. What can we do that's different with the technology? And at the same time, we tried to think about, we need to continue to scale the technology. So here's another little technical diversion to give you an idea of the challenges we faced. One thing we found in getting these products accurate is this is a cross-section of a product in plastic. So what you're looking at here, this is the molding compound. This is the black plastic that you see. You probably didn't know it's comprised of all these bubbly things, right? But this is what it looks like. And this is the top of our chip. So this is the last metal layer here. That's the molding compound. And that molding compound gets in between the windings of our coil and the windings of the interconnect on the die. And so what happens is you have fringing electrical fields out into this molding compound. So if the permittivity of that molding compound changes, then the capacitance changes. And if the capacitance changes, the frequency changes. So what I'm ultimately saying is the package can shift the frequency. You know, who would have foreseen that? Similarly, the B field, or the magnetic field, is fringing out of the product. And anything that modulates that can change the frequency. So like I mentioned here, I just presented all these effects just last spring. We've solved them 4 years ago, so that's usually how these things go. But this is what it was. You know, what we did is we're looking at it this way. So this is looking at a cross-section of the die. So you see the die here, okay? This is the fringing B field. You have an inductor, so it has a magnetic field that sprays out. You have a parasitic capacitance that sprays into the package, and then you have the bond pads here. We developed a Faraday shield technology where what we did is we backside metallized the wafer. Then we built a topside metallization with a dielectric standoff, or a mesa. So basically spinning on material to move this metal shield away and then put plated copper over it. And that contains the B fields. And then it terminates the E fields. So the capacitance is no longer stray. It's terminated to this Faraday shield. And then we were able to actually make the die very thin, which is something we found customers were interested in. And this is how our product looks right now. If you go to IDT's website, they like showing these pictures because they're very unique. When you look at our wafer, this is what it looks like. This is the Faraday shield that's processed on top of it. And then this is actually an example in a customer product where you see our die here stacked on top of another die. So as I mentioned, I presented this last year, and this was a very exciting way to make a self-contained die that was effectively entirely encapsulated and could support these types of frequency accuracies. And we found these great high volume applications. So this is a USB mini card reader. So this is the product you stick into the side of your PC, and then you read off the SD micro cards and other memory cards from your different consumer products. It's a very simple product. On one side, it has the controller and some passives. You can see those here. And on the other side, it has the connector and the crystal. And so this is what our customers started doing with our products, which amazed us. They would take that controller product, and then they would stack our die on top of their die. So what you're looking at here is, this is that package, this package here, dissolved away. And then inside is our die, and on the bottom is the customer's die. And so this product embodiment has been hugely successful because it has a very strong value proposition. It goes back to that IP business, right? Here, it's like now our customer can sell this product and it doesn't need that external crystal. We're not doing replacement anymore. We're actually enabling something new. And the other thing that I realized is, you have something when your customer starts doing something new. Nobody had done this before. And it amazed us. We have about 25 customers now in high volume doing this right now. When we first thought about it, we thought, no, people would have to be crazy to do this. And they do it because they can differentiate their product by getting rid of this crystal. So it became very exciting. And we had to develop a lot of technology to reduce the cost to compete in these high volume markets. So we developed these production test algorithms to test and trim the product in very minimal time. And there actually ended up being almost as much technology in product test as there was in the chip design. And let me give you an example here. This is actually our original test platform. It's a 64-site platform. We would insert the devices in there and then test them in a chamber. Then we moved it to an operator-driven platform. And you can see this phased approach is what enabled us to finally get to high volume, and it's not like research. I always tell people, the way research works, this is how my dissertation worked. I made one good enough to graduate. That's how research works. That doesn't get a laugh here. There's no PhDs, I guess, right? Yeah, so by the way, since you're undergrads, when you talk to graduate students, I guarantee you, that's how they graduate. They just make one work long enough to get the data and get the hell out of here. Unfortunately, in industry, you can't get away with that. And where we ended up here is this. We have built a custom MEMS probe head here. It tests 126 sites, 126 die of ours at the same time. And our throughput is 30,000 units at 2 temperatures in 1 hour. So we went from this, which took about 15 hours to trim 64 devices, to this, which is now production, 30,000 units in 1 hour. So it was a tremendous amount of technology. And just as we were figuring that out, we were sitting here, wow, look at all this VC. This is awesome. And that wow went to ow. I mean, you see how bad this is? I don't know if you guys read this in the news. It's awful. There's no money. It's gone. It's really bad. This is like the 2001 thing all over again. And so there was literally no money. Actually, what was happening is, so limited partners, they're the ones that put the money into, they're basically, individuals or pension funds or endowments. They fund these venture capital firms. And what really technically was happening was they have charters where they can only put so much money at risk. And with the stock market crash, then they were out of spec on what they could fund VCs. So the VCs would call, okay, time for funding, and they couldn't put the money. So there was literally no money. It just totally froze. And the few funds that did have money presented us with terms that were, frankly, just very unfavorable for management. We still had no meaningful revenue since the IP business, but that die business, that stacked die business was really starting to take off. The board and the management team were debating the leadership role. This was a big challenge. And IDT, amongst many other companies, actually started to see the opportunity with where we were with the product and what they could do with the technology. Frankly, I was kind of getting tired of everything, but luckily, what we had been doing is pursuing a merger for well over a year. And this is something I'll highlight later. And as we're doing all this, guess what happens? The world doesn't stand still. So I showed our product here. This is our 0.13 micron product that was taking off. Then guess what happens? Silicon Labs, a public company, announces the same technology. You can imagine, we're a little startup in the middle of the financial crisis, trying to get our bearings. Another company announces same technology. So what do we think? We think, shit, we're screwed. But we were acquired by IDT. So we were acquired by IDT because what happened was the management team recognized that this was the best exit to keep growing this business. And I can tell you, it's been an interesting experience. It was a very clean acquisition. You know, the whole company joined IDT. IDT saw the value proposition very clearly, and they're the market leader in what's called silicon timing products. So these are products that take frequency references in and then generate multiple frequencies out. So they don't do the reference itself, but they do the buffering and the multiplication. So PLLs, phase lock loops, basically. And it's kind of an unusual exit these days. So they put me in charge as the general manager. So the founder moving to the lead operator and manager is actually very unusual. And at the same time, the entire team remaining to grow the business. So that's why I called this talk "Exiting Back onto the On-Ramp." You know, we've been fighting for our lives, and then we go through all these things where we think we finally have the product, and then, you know, now we're at IDT, and now we're actually still doing the same thing, just with a different label on top of us. And for me, I've experienced a lot of differences being a general manager at a public company versus being at a startup. You know, you have to answer with real numbers to the street. You can't sell bullshit to VCs. So it's a totally different ballgame there. You're held accountable for results. And in the end, you know, what the management is looking for is to grow the business, grow revenue, grow products, or what I call turn the crank. It's a cycle. Okay, you got that product out, get those customers, get that revenue, now revise that product. What's the next feature set? And it's been going much more rapidly at IDT, even though we're our same organization, than it did actually as a startup. So frankly, it's been a lot more difficult than it was as a startup. Here's just an example of some high volume design wins that we're shipping into now. This is I don't know if you've seen these products. This is what's called a USB drive-in package. They're coming to America. They're everywhere in Asia right now. It looks like a little piece of Trident gum. The whole USB drive is that small, and there's no connector, just the exposed leads, and you just stick it into the side of the drive, or in the side of the port. So this is what it looked like before IDT, and what you see here is, of course, the crystal. You see the controller, and you see the memory. And then once we showed up, you know, of course, the controller and the memory are still there, but now you can see our CMOS oscillator replacing that. And this is also significant because this is a packaged part. It has to go through a solder reflow process. This is a silicon part. It gets stacked and wire bonded. And then this whole thing is just injection molded. So it's a very significant advantage to eliminate that crystal and move to our silicon product. After 1 full year at IDT, we've really announced some groundbreaking products. We did finally develop that 100 ppm oscillator. It's been in the news. It's been covered by EE Times and other periodicals. And that die product that I mentioned has really taken off, and it's the only product of its kind in the world. Others are looking to take a chip away from our business, but I think we're the only ones that have the whole technology figured out. We've shipped over 6 million units since the acquisition, which was just a year ago. The CMOS oscillator technology is now becoming mainstream and replacing quartz in a myriad of applications. We have solar panel design wins, these USB product design wins. There's actually these products we go into, I don't even know where they come from. They're just sort of random and all over the place. And we continue to expand and grow our business, which is exciting. And it's actually been a lot easier to do at IDT than it was as a startup. And we'll continue to grow our business and introduce many more exciting products. So I'll leave you with just a few thoughts here as we wrap up. I wanted to kind of illustrate success is it's kind of cyclical, or it's kind of like a circle. I mean, you start and you have to be optimistic, but I hope that what I'm showing you here is you also need to be realistic. And I wanted to show that these technology-based businesses, it's a push, it's not a pull. You don't know where the product's going to go. So you have to manage the risk. You have to figure out, okay, well, this is what I'm capable of doing now. Where can I deliver that product? And can I generate revenue? And then can I iterate and come back and continue to refine it? You also have to think through the product and the value proposition. You can see some of the errors in our thinking. We did all this work and then defined a product that was a replacement product. There wasn't a very strong value proposition for that. And frankly, sitting down and spending more time thinking that through would have saved a lot of execution cycles. But like I say, like I wrote here, accept that it's iterative. And then once you start, you have to execute. Do as much as you can with the money that you have or the resources you have. You can see when I started this thing in Michigan, we started and we had this IP business. It didn't turn out to be a sustainable business, but it proved that we could replace quartz and that we could actually build something that was competitive. And that's what got other investors interested. And we have always aimed to stick to the plan. It's very easy to get distracted in other areas, and this is something that drives me crazy, this Messiah complex. I talked about it with the VCs that brought these guys in. There is this mentality in the Valley, oh, we'll just get this perfect guy who will execute. To me, it's just hiring mercenaries. The people who fight for their country are the citizens of that country. They're not mercenaries, right? That's what this attitude is. So my advice is completely ignore it. I think it's total crap. And be confident in what you're able to do. But at the same time, learn from the mistakes that you make and adjust your execution. Don't be blind, but be confident. And then survive. For me, one of the toughest things is these random external factors can just blow everything up. The financial crisis, who the hell saw that coming? Certainly when we have our heads down working on a semiconductor business, we're not thinking about credit default swaps and things like that. But that's why it's the hardest thing to deal with. At the same time, there are things you can see, competition, other factors that will affect your business, and the upshot is always hedge. So this is the point I was alluding to earlier. The reason we had a clean exit is we had been talking to potential acquirers for well over a year before the board ever came to us and said, okay, let's go the acquisition path, because we had seen that there was risk coming. So to manage that risk, we wanted to make sure we had another hand to play. That's a critical thing to success. And then it just keeps going, like I said, turning the crank. The reality of entrepreneurship is, I tell people it's not glamorous. It's actually, sometimes it's just flat out awful. I was giving a lecture at Michigan, I told students, when you're in a car accident, hopefully not many of you have been, or any accident, you fall out of a tree when you're a kid or something, and there's that moment that time just stands still because you know something awful is imminent. That's what a startup feels like all the time. Okay? It's not a good feeling. And the fact is, other careers are actually a lot more lucrative. I mean, you can do other things with a lot less risk. I mean, hell, you can be a banker, right? I mean, those guys are back in vogue these days. But the thing is, just be aware of it. I don't like a lot of rah-rah preaching about become an entrepreneur. It has to be right for you, and you have to know what you're getting into. I'm an optimist but a realist, and the thing I'm trying to show you here is we fought for everything that we achieved. There's still a lot of luck in this thing too. I mean, the Mobius exit was unlucky in the sense it wasn't in a bubble, it was in a desert. Had it been in a bubble, we would have exited for 10 times the purchase price that we exited for. But we were able to exit in the worst financial crisis since the Depression because we had a great technology and a great product going into a huge market. That was why we were able to. But the fact of the matter is it's pretty frustrating, right? The price would have been very different at a different time. And I sometimes struggle with this. I struggle with a passion for doing real, what I call real engineering, real products, versus chasing social media and other hype. But that's also part of the introduction I wanted to give you. I remember 1999 versus 2001 vividly. And I think we're going through the same cycle right now. In the end, it's a value system. It's a personal value system, what matters to you, what you want to do in your life. And it's a company value system. Companies that build value will always have opportunities. Everything else is just hype. That's what this stuff is. And like I said, I think 1999 might be repeating itself all over again. So a few parting comments. These are just two quotes I like. In the long run, men only hit what they aim at. Therefore, though they should fail immediately, they had better aim at something high. It's Henry David Thoreau. And what that says to me is nothing worth doing is easy. And failure is an intimate part of success. So you have to pick yourself up. But it also says if you're going to do anything at all, you better do something meaningful. Another one that I like is genius. That power which dazzles mortal eyes is oft but perseverance in disguise. And I really like this one, and I hope this story shows you why. Here's a quote that was recently said to me. Someone said to me, Michael, some people wait for markets to arrive or technologies to mature, and others make it happen. I thought I'd be retired by the time CMOS threatened quartz, and you have ruined that dream for me. CEO of a crystal company. So tomorrow, I'm available to talk from 9 to noon over in 159 Everett. So I encourage you to come by and ask any questions you have. I'm happy to discuss anything on entrepreneurship, semiconductors, technology. And go Illini. Any questions? Their product is still in the market, and we compete with them. Yes. Okay. And I guess I'm supposed to announce there's a 6 o'clock event here for the Lemelson MIT Student Prize, which I guess is going to be announced tonight. So enjoy. Thank you for your time.